As another example, Karatsuba integer multiplication, which is described by the recurrence relation 3 times t of n over 2 plus big O of n. It meets the condition that alpha is 3, b is 2, and d is 1. So therefore 3 is greater than 2 to the 1. And the runtime is described as big O of n to the log 3, which is n to the power of 1.6. So all of our cases for the master theorem can be used to derive the asymptotic notations for all of these algorithms. So what we have learned is that branching in the recursion tree causes the number of problems that are at the bottom to explode. If you have a high level of branching, it means that more work is done at the lower levels of the tree, and therefore you have a higher runtime. And this is the case where your runtime might be quadratic or even cubic. While if you have less branching, it means that less work is done at the lower levels of the recursive tree. And this is the case where your overall runtime will be dominated by the top levels of the recursive tree, and overall you would expect your runtime to be lower. So this is the case where you might find algorithms that are big O of n. But these are just general guidelines, and of course there are many different algorithms with many different recurrence relations. But of course these are just general guidelines, and there are several different But of course, this is just the intuition behind the different cases of the master theorem, and there are many different algorithms with different recurrence relations, and every algorithm might have a different computational complexity. So what we have learned is that the master theorem allows you to analyze the runtime of recurrence relations, and basically it gives you quick codification for calculating an asymptotic notation, which otherwise you could do from scratch, but that it would take you too much time and effort to compute from scratch. Now there's one case when the master theorem does not apply, and this is for the third case where I mentioned you need to check that this condition is actually satisfied. So you need to find a constant c which is less than 1, such that c times f of n is greater than or equal to a times f of n over b. Now while this condition is satisfied by most polynomial functions, you, just for the sake of correctness, you have to double check that this regularity condition is actually satisfied when you state that the particular case of the master theorem is what applies to a recurrence relation. The substitution method is a simple method for solving recurrences, and it comprises 3 steps. Basically, you guess the solution in terms of big O, and then you substitute your guess solution to smaller values of the runtime t in your recurrence function, and then you just do the math to show that if you assume that your big O guess holds for the smaller values of t, then it must also hold for the larger values of t, like t of n. So this is essentially just like induction, where you assume that your inductive hypothesis applies to the smaller values, and you want to show that it has to be true for the larger values as well. Let's look into this example of using the substitution method to prove an upper bound on an algorithm's runtime. Let's say that our recurrence relation is t of n equals 2 times t of the floor of n over 2 plus n. And let's guess that the solution is maybe T of n equals big O of n log n. What our guess implies is that the runtime at input n is less than or equal to C constant times n log n. And in turn, what this implies is that the runtime at input floor of n over 2 is less than or equal to constant C times the floor of n over 2 times the log of the floor of n over 2. Now, the approach that we take with the substitution method is that we take this inequality, the runtime at a lower input that our guess would imply, and we substitute it into our original recurrence relation in place of the t at the lower input. So in other words, we replace this runtime t at input floor of n over 2 with c times floor of n over 2 times log of floor of n over 2. And this gives us this inequality. The runtime at n is less than or equal to 2 times our formula that was implied at a lower input plus n. And if you solve this, this becomes less than or equal to c times n log of n over 2 plus n, which equals c times n log n minus cn log 2, because log of n over 2 equals log of n minus log 2, which equals cn times log n minus cn plus n, and that's because log of 2 equals 1, so that gets removed. And that is less than or equal to cn times log n, which is exactly what we had to prove in the first case. So our goal was to prove that according to our assumption, the runtime at input n would be less than or equal to cn log n. And this is exactly what we were able to derive here. So in other words, we started from assuming that the inequality holds at a lower input, and from that we were able to derive that indeed there is no contradiction and the inequality for the runtime does hold at a larger input n. So in other words, we used the substitution method to prove that the runtime at n equals big O of n log n.